Look at this enterprise terminal interface. When an employee asks the AI for last week's revenue numbers, the system outputs a confident but entirely incorrect number. This failure occurs because the AI relies on parametric memory. It is drawing solely on static weights formed during an initial training phase that ended months or years ago. When the factual memory in those weights is exhausted, the system architecture continues to synthesize language, creating plausible fictions. In technical terms, this is known as a hallucination. This diagram illustrates the constraint. A standard large language model treats every prompt like a closed book exam. Its reasoning process strikes a wall the moment it requires data created after its training cutoff. Attempting to fix this by retraining the model weights for every new company report is often impossible. Updating those parameters requires massive clusters, weeks of processing time, and millions of dollars per run. Consequently, static models cannot affordably process dynamic enterprise data without a change in their underlying architecture. The solution relies on a specific architectural change, decoupling knowledge storage from language generation. We execute this using Retrieval Augmented Generation, or RAG. The architecture introduces an external database node to the environment. This provides an ultra-fast research assistant, leaving core LLM weights untouched while intercepting the query to instantly hand the exact reference pages to the model. Providing verifiable data within the prompt context suppresses the model's tendency to hallucinate. To bypass the memory limit, the system splits the AI process into a two-stage pipeline, retrieval followed by generation. In this first phase, the user's query bypasses the LLM entirely. The system routes the input directly to this external storage vault. This vector database is a secure vault specifically designed to hold proprietary company documents. Inside, documents are stored as embedded geometric nodes. Your PDFs, emails, and code bases are mapped across a high-dimensional mathematical space. When a query arrives, the system performs a similarity search. It scans the space for document nodes closest to the coordinates of the query's topic. The scan highlights a specific isolated cluster of nodes that match the user's intent. The system extracts specific chunks of text, individual sentences, or paragraphs, rather than entire dense documents. These document chunks are then pulled from the vault to be used in the next phase. Chunking the data is necessary to manage context limits. This ensures the AI receives relevant facts without being overwhelmed by high volumes of irrelevant text. This retrieval process isolates the required information in microseconds. Because the search is based on mathematical distance rather than exact keyword matches, the database can identify relevant concepts even when the phrasing differs. Phase 1 effectively distills a vast corporate archive into a targeted packet of verifiable facts. In the second phase, those extracted facts are finally delivered to the core AI model. This assembly window shows prompt injection or stitching. The system combines the user's original query with the extracted document chunks into a single unified data payload. This context-heavy payload is then sent directly into the core LLM. The system applies a strict instruction to the model. It must use only the provided chunks to formulate its answer. This constraint overrides the model's reliance on its own outdated parametric memory. In this configuration, the LLM functions as a reasoning and language synthesis engine, drawing its facts from the external vault. The model summarizes the specific text it was just handed, grounding the final response in documented facts. This grounding process makes the output verifiable as the AI cites the specific sources injected into the prompt. Users can trace these citations back to the original corporate PDFs or internal emails. The system produces this accurate, updated response without adjusting any of the underlying weights in the base model. Phase 2 ensures the AI operates strictly within the boundaries of verifiable corporate reality. Shifting from the internal mechanics to the macro-level outcomes reveals the impact of this architecture on an enterprise. This three-pillar breakdown shows the advantages of RAG over fine-tuning. The first pillar is zero retraining costs. By bypassing model retraining, organizations save the significant financial and computing resources typically required to update an AI's knowledge base. The second pillar is real-time updates. Notice how the PDF goes directly into the vault. Updating company information is as simple as adding a new file to the database, allowing the AI to access new facts instantly. The third pillar is complete access control, represented by this padlock, securing the external database layer. Administrators can restrict access to sensitive documents at the database level. The LLM never sees the data unless the user has the proper clearance to retrieve it. This architecture solves the problem of hallucination through targeted data routing. The entire system can be summarized by this equation: RAG equals smart retrieval from a database plus the fluent generation of an LLM. Ultimately, this is the essential structural bridge allowing foundational models to power modern enterprise operations securely and affordably.